I hope you got a good introduction with an experiment and with a numerical about the law of conservation of momentum. Here we're going to see the law of conservation of momentum in detail. First is the statement, the official statement that you need to write in your exam. In an isolated system, that is where there is no external force like friction or friction by air or anyone pushing it or pulling it, if there is no external disturbance, the total momentum remains conserved. Right? Whatever is happening within the system, the total momentum before and after whatever is happening, it will be conserved. Mathematically, it looks like this. Initial momentum of the system is equal to final momentum of the system. So mathematically, if I have to use variables and everything, it would look something like this. It can be any number of things, right? It will be equal to the same things or summation of things, and it would be so. Again, it can be just a single term or it can be a zero in some cases being equated to a single term or a zero or any number of terms. Mathematically, it will look like this. As a proof, we would be just taking up two objects, and this is how the proof starts. Suppose two objects, two ball A and B, say, right? We'll name it as A and B, of masses MA and MB are traveling in the same direction along a straight line at different velocity, UA and UB, respectively. Here UA is greater than UB. So we have three scenarios: before collision, during collision, okay, I'll write it over here, during collision, and can you guess the third one? Yes, after collision. So before collision, what is that we are looking at? We have object A, object B having a velocity of UA and UB. So mass of this is say MA, this is MP, this is your initial scenarios. Basically at t is equal to 0. And at some point of time, there is a collision of these two objects. So they exchange some kind of force, right? As per third law, what is that it tells? For every action, there is an equal and opposite reaction. So these two forces will be equal in magnitude but opposite in direction. This is what happens during the collision. And after the collision, the objects may move like this. This having a velocity of VA and this having a velocity of VB. So this is your entire picture before, during and after collision. Now, mathematically, how will it look? So before collision, right, the momentum would be what? MA UA and MB UB. After collision, the momentum is MA VA and MB VB. So we need to prove that those are equal. Actually, let me not make it too complicated. Let me just write in what is that we need to prove. We need to prove that MA UA plus MB UB is equal to MA VA plus MB VB. Okay, how will we do this? With the help of the first and the second law of Newton, the proof. So as per the first law, right, as per the second law, sorry, third law, not first law, third law, FAB is equal to FBA, is it not? In terms of magnitude. As per Newton's third law of motion, we have FAB is equal to minus FBA. So this is nothing but force exerted on B because of A, and this is nothing but force exerted by B on A, right? So we know that force is nothing but mass into acceleration. So FAB over here is nothing but the force exerted on B by A. Right? So that would be nothing but mass of B and acceleration that would happen in B after the collision. This would be equal to MA into AA. We're just writing individually what will happen. That's it. Don't think too much. This is what it is. Now, what is A acceleration, right? Acceleration is nothing but V minus U by T. Change in velocity with respect to time is A, right? So we have to substitute this. So let me write it a bit neater. Let's substitute AB being equal to, or A being equal to V minus U by T, right? If I substitute in each of this, what will happen? MB into VB minus UB by T. T is the time of collision. It will be just a fraction of second, but T is time. Minus MA into VA minus UA by T. Here T is time of collision. T is time of collision. See, time of collision would be same for both, is it not? It's collision, obviously. So both the T's will get cancelled. So basically we have MB into VB minus UB is equal to minus MA into VA minus UA, right? So time and time got cancelled. So now all we have to do is use distributive property. VB minus, okay, don't get confused, this is VB minus MB into UB is equal to minus of plus is minus MA VA, minus of minus is plus MA UA. Now we will just have to rearrange. Take this negative term to the right hand side and this negative term to the left hand side. So we have MB VB plus MA VA is equal to MB UB plus MA UA. LHS is equal to RHS, right? Is it not? This is what we had to prove. I mean, we actually proved that LHS is equal to RHS, and this is what we had to prove. Hence, proved. Right? It's very simple picture. It's a very simple derivation. This is as per second law. Okay, again, it can be any number of things, or it can be just a single thing, or the system is entirely stable at the start, so it will be zero also. What? The left hand term and the right hand term, any one of it or both of it. It can be anything. It can be any number of terms. Please understand that. It need not be two, remember. So for an isolated system, that is without any external force acting on the system, the momentum is conserved. And this is your proof.